So in today's video, we're going to go ahead and take a look at how we can use arcsin of x in order to simplify our integration process. And so previously, we actually took a look at how we can use arctangent of x. Just a little bit of a review. This is essentially what we did. We essentially want to get it in the form of the derivative of arctangent of x as we did over here. And so then when it comes to arcsin of x, it's essentially just the same exact thing, except it's a little bit different because this one involves square roots. And so here, when we take the derivative with respect to x of arcsin of x, we end up with 1 over the square root of 1 minus x squared. And then when we take the derivative with respect to x of arcsin of ax, we just get a over the square root of 1 minus ax quantity squared. And so really all that we're going to do is we're just going to extend this notion from tangent of x, from arctangent of x, in order to find these in order to really integrate these rational functions that involve square roots. And so let's just go ahead and do that. So over here, we have a very basic example to begin. We have the indefinite integral, the indefinite integral of dx over the square root of 1 minus 4x squared. And so essentially, what we're doing over here is we're just going to try to get it into one of these forms that we saw over here, either this one or this one. And so let's go ahead and see what we can do. So here we have 1 minus 4x squared. We can write this as just essentially 4x squared is really just 2x quantity squared, right? And so that can kind of help us get it in this form over here with the ax quantity squared. So this just becomes the integral of dx over the square root of 1 minus 2x quantity squared. And so the next thing that we can do is we want to just get this, we can try to get this 2x over here to just be one single variable. So we can just do a quick u substitution. We can say let u equal to 2x, which would tell us that du is equal to 2dx, right? And so then if we want to go ahead and get a 2dx over here, we just put a 1/2 on the outside times the integral of 2dx over the square root of 1 minus 2x quantity squared. Right? And the reason why we're doing this is we just want to simplify it as much as possible, because really we can take this integral over here and just get it in this form of 1 over the square root of 1 minus something squared, 1 minus u squared in this case. And so now that we've kind of done all this little manipulation here, we have the 2x over here, so we have a 1/2 on the outside. We have the 2dx here, which is just going to be equal to du. So that just becomes du over the square root of 1 minus 2x we said was just equal to u, and so this is just going to be equal to 1 minus u squared. And then finally, this right over here is just going to be equal to 1/2 times arcsin of u plus c, right? Because this right over here will just be arcsin of this input, which is just going to be u in this case. And then finally, we back substitute to end up with x again. We get 1/2 times arcsin of 2x plus c. And that right over there would be our final answer. So very basic example, but a very good way to sort of illustrate the process of how we would do this. And so now let's go ahead and amp it up a little bit. Let's do a little bit of a more advanced question. So here we're taking the indefinite integral of secant squared of x over the square root of 25 minus tangent squared of x dx. It's a little bit more intense looking. But really, we just have to observe a couple of things. This 25 over here is a perfect square, and so is this tangent squared of x. So why don't we just try to factor out this 25 from the denominator? And then, so we'll ultimately end up with the integral of secant squared of x over the square root of 25 times 1 minus tangent squared of x over 25, right? And then dx over here. And so this is ultimately going to be equal to, we can take this 25 out. We get the integral of secant squared of x over 5 times the square root of 1 minus, here we have tangent squared of x over 25, but isn't that really just tangent of x over 5? And then we can square that dx, right? Because you distribute that square, you get tangent squared of x over 25. And so now we have a couple of things we can do. We can just go ahead, we have this tangent of x over 5, we have secant squared of x over 5, and so we just need to observe something. If we make a u substitution, we let u equal to tangent of x over 5, then this will tell us that du is equal to secant squared of x over 5 as well, and then dx, of course. We have secant squared of x over 5 right over here, and we have a dx, and here we have tangent of x over 5, and we're squaring that. So we can make a very good substitution. We can just say, if we do all of this, the secant squared of x over 5 times dx, that's just du. this all disappears, just becomes du. Here we have the square root of 1 minus tangent of x over 5, and we're squaring that. That just becomes u squared, right? So that right over there is our substitution, and now we can go ahead and just integrate. And so if we're integrating with respect to u, this ultimately becomes arcsine of u plus c. And then we want to get it back in terms of x, and so that's just going to be equal to arcsine of tangent of x over 5 plus c. And that right over there would be our final answer. So this is a very, very good example. By the way, both of these examples are courtesy of Levin Logic's AP Calculus AB worksheet, and so definitely check that out. But yeah, here are just a couple of examples of how we can use arcsine in order to simplify the integration process for these complicated looking rational functions. And so there are many different examples we can do. So I definitely encourage you to really get comfortable with this topic, because it's a very, very helpful integration tool for these complicated rational functions, as we saw over here in this case. So you just really have to get good at recognizing how to sort of obtain these different forms of these derivatives of inverse trig functions, especially arcsine and arctangent, because these are probably the most common ones you'll come across in, Calculus 1 and Calculus 2. So I hope this helps.